Okay, so from last time, now we're just negotiating about what language we're going to use. Okay, from last time we talked about what is going to be the pipeline for machine learning. So in machine learning pipeline, usually you have about 4 steps. So firstly, you have your data. And the first thing that I'd like to ask you to do is to actually look at the statistics of your data. Because sometimes, for example, if you work on time series information, right, you may see that your data behave in a periodical way. Like it has some kind of periods that it maybe, for example, we look at the irradiance from the sun, like the sunlight strength. And the thing is, the sun may be really strong in summer and really weak in winter. And because of that, if you look at the period of your data, you may see that, okay, the distribution of your data is not homogeneous throughout the year. It's not the same. So what you may have to do first is to think about how would you split your data into training, testing, and validation. Ideally, you should, okay, regardless of what your data might be, what you should do is to split your data into 3 sets, and all of those 3 sets, each of them has these homogeneous properties. For example, okay, let's go back to the sun radiation again. Okay, we know that the strength of the sunlight is strong around summertime. Let's say this is summertime. And then winter, right? And we have some raining season. Okay, the sun may be really strong around summertime. And then it goes pretty deep down around rainy season and maybe come back a little bit around winter. So what I might ask you to do, okay, I'll just say this is irradiance, is to actually split your data into this training, testing, and validation, kind of homogeneously. What do I mean by homogeneous? What I mean is that, okay, firstly, maybe you should evenly sample your data in each case. For example, from summer, you may evenly sample some of them, put it in your training, and then sampling them again in winter, and sampling them again in rainy season. So what you would have is that, okay, so for your training, you have some cases from summer, some cases from rainy, some cases from winter, and you should do the same for testing and validation. With that, what you would have is that you will have homogeneous data set, because your training, your validation, and your testing, each will have equal amount of cases for summer, rainy, and winter. So that's the first thing that you should do. You should split your data evenly and think about what is the key feature that will make everything homogeneous. Like in this case, if we talk about sun radiation, of course, we know that summer, rainy, and winter is going to be the key. But what about if you are working on, let's say, like one of our friends, he works on types of the trees. Perhaps you should look at trees in each location in Thailand because the types of the forest is different. So you should evenly sample each of those cases and put them in training, testing, and validation. So that should be the first step. After your first step, then what you should think about is to do feature selection. Sorry, not this one. Feature selection, or maybe denoising. So that's another thing, but I didn't write it here. But we will go through each of them. Feature selection or denoising. What's feature selection? Feature selection is a process where you select which information from your input is the most important. But we will see the example today. What you should do next after you do feature selection is to remove all the noises. What is noises? Noises like outliers. For example, let's go back to our irradiance data. Suppose that there was a day that you have a very heavy dip right? All of a sudden, it goes down like that. So it shouldn't happen in summer. Things shouldn't go that way. So yes, part of your work is to actually remove the sample out of your data set. That means you wouldn't consider anything that behave in an abnormal way. And the reason is because sometimes this abnormality happens because someone maybe suddenly turn it off, someone maybe close the shade around the area. It's like an indicator in my case because I actually took pictures of the sky. Sometimes there's a crow flying and land on my camera, and it's kind of like this is going to be my next nest. So that is something like I have to do. I have to remove those pictures that involves things that I don't like, or the things that is going to be unrelated to my work. So that is what denoising means in your data pre-processing step. Okay. Are we all okay? Yeah. After we do data pre-processing, after we have our data split, next thing that you may do, but not that often these days, is to do what we call feature extraction. So feature extraction is like you trying to find a new way to represent your data. I believe some of you here take class in image processing. Can you raise up your hands? Yes. If you took class in image processing, there are going to be bunches of data transformation that going to enhance the way that you use the information from your image. And those transformations are, for example, Fourier transformation, wavelet transformations. What else? Discrete time cosine transform. There are many. And in fact, our deep learning can be used as those transformations as well. So the feature extraction is more like you have your data. You don't want to use it directly onto your machine learning, but you want to extract some important information. So that's what feature extraction is like. Mm-hmm. After you have your feature, everything ready, then you will deal with your model. That is, first, you will train your model. But today we will see what it's like. You train your model. After you train your model, of course, when you train your model, if our model will only contain like a weight of the model parameters, you probably just fine by training model and then do the testing. You can just skip the validation. You can directly do it like that. You'll be fine. But the thing is, in almost every tool in machine learning, including deep learning, you will have what we call hyperparameters. That is like the settings that is going to be somewhat could impact your work. For example, number of iteration, number of epochs you want to run, or maybe your stopping criteria. Those stuff are actually your hyperparameters. So we need validation, or even for machine learning, for deep learning, number of layers is going to be your hyperparameters too. So in order to choose that wisely, people need to do the step that we call the model validation step. And actually this is going to be like the important thing that we're going to learn today. That is, how can we validate our model, and what are the different ways that we can process our data and make it consistent with the result. Because model validation is actually very similar to testing. That is, you run inference, and last time we talked about what is an inference. We run an inference on our data and we get the result. In our testing and validation, the only difference in our validation is the fact that we are sorting over each value of your hyperparameters. And we want to use the validation dataset to pick the best hyperparameters for your case. And that's the reason why we need model validation. We cannot do it directly on our testing. The reason is because otherwise we are going to be overly positive about our choice. Because your testing should be the one that you will use at the end to say that this method is better than others, or maybe than your state of the art. In machine learning, we have a word called SOTA, SOTA, which is shortened from state of the art. Or in a simple terms, it's actually your comparison method. So it's something like your baseline model, baseline work. For example, if you've been working on deep learning, you probably heard of tools like support vector machine, which is usually being used as your baseline. So alternatively, sometimes people refer to SOTA as baseline. But the underlying meaning of baseline is like it's a very traditional method. But the SOTA is the new one that maybe just came recently before your new work. You know, like the year before, like year 2024, it's going to be a SOTA method, and your current method is your proposal. But you may want to also compare with other works that came before, like in 1980s. Those are going to be your baseline or your traditional comparison. So yes, in this comparison. So in this lecture, there are so many terminologies. But yes, because data scientist is being known and probably used a lot in companies, so there are more and more like people use vocabularies, and perhaps this course will help you understand some of those words, especially when you go to work. Or when you have the interview and you know what they are referring to, like an inside knowledge. Anyway, so yes, we now know what's the importance of the testing. After the testing, model training, validation, one thing that we need to learn is how we are going to evaluate them. And yes, this is the topic that I left last time. And we are all very silent and sleepy. Is everything all right? Still okay. หรือน้องพ่อพอใจภาษาไทยมากกว่าคือพี่ว่าภาษาไทยคล่องมากเลยโอเคใช่ไหมให้ว่า English ต่อ Okay. Now I'm just checking the entire class if they're still fine. Yeah. Okay. So today we will talk about the model performance or evaluation techniques. And by the way, these are going to be techniques that you use for maybe general work like regression task. What is a regression task? Regression task is pretty much another word for estimation with model training. So it's like you feed in an input and you want to use that input to estimate something at the current time step. That is called regression, which is different from prediction. Prediction is the term that we often use when you are using the current information to predict whatever is going to happen in next maybe 5 minutes. That's predictions or forecasting. Just know. Yeah. So the following evaluation will be used for regression, forecasting, predictions, but not the classification task. But some of them may be having some kind of overlap in between, But anyway, so that you know what you are doing. Because when we are learning classification tasks, we are going to have another set of evaluation matrix. For example, if you heard of F1 score, right? F1 score, precision recall, those stuff. Micro, macro, whatever. Yeah, those are going to be the evaluation matrix for classification task. But for today, what we are going to learn is pretty much for the simple regression and predictions. Or other words, it's actually for the fact that when your output is going to be like a scalar value. And just that. So therefore, the following assessment is going to be like a very fundamental one. And congratulations to those that studied estimation theory before. Some of them will be easy, especially the theoretical part of it. But we will extend from those course, by doing the evaluation that involving using empirical samples. Okay. So yes, we will do the measurement through theoretical properties and the measurement through sampling distributions, or maybe sampling from distributions. That's what I mean. So the following 1, 2, 3, 4 are those evaluations that people normally use empirically. But yes, they will somehow involve with some statistical properties. So you just have to be careful. But just know they are normally used for empirical result. But of course, some of these theoretical properties can also be used with your empirical result as well. That is the MSE, the mean square error. So after the lecture today, I would like you to remember one thing. When people talk about mean square error, it could mean mean square error in theoretical sense and mean square error in the empirical sense. There are two ways to think about it. You have to be careful.ขอโทษนะคะ เอาละกู Empirical or theoretical, there are two ways. But in all of your machine learning world that you're going to do, after you run the experiment, do the implementation, get the results, you will all do the empirical mean square error. But you will use some of its theoretical properties to explain certain behaviors. And those behaviors are going to have a name. We have a name for it. We call it high bias or high variance. But you will learn about those terms today. It just helps you explain what happened in empirical world. But yes, today we will learn that. Okay. Shall we go? Shall we go? Are you okay with everything? I try my best. Don't drop from this lecture today. It depends. As long as she lives in this class, it will be in English. But if she's gone, it will all come back to Thai. Is that okay? You gotta stay. Oh no. Okay, just kidding. Right? From theoretical world, in our setting, it usually involves with the fact that yes, we have an input, feed that input into a function. And this function is our representative for the machine learning. And then y hat is going to be our prediction or predicting value. Maybe just let's call it predicting value. And sometimes when people look at a machine learning model, they may think of it as in, because we are receiving an input and this input could have some kind of statistical behavior. Therefore, we will say that each input that we feed in is like an ensemble. Ensemble. Do you feel familiar with the term? Ensemble. Okay. Ensemble. It's like a sample. A random sample, or maybe a sample of a data from a distribution. Or on the other words, you can say that, we know that the image, let's say, of pet is X. But that pet could come with various, like shape and form. Because it could be like a dog, a cute dog, an ugly dog, or maybe a cat. Therefore, if all of them still call pets, they are pets. So therefore, you may say that, each of that variation is xi up until xm. And this m, we could say that there are m samples or m random sample. And let's say if the more picture that you feed into your system would give you, a more precise result. Of course, there are cases like that, especially if you are doing work with, let's say, forecasting, right? The more lags you have, and each of those lags are actually one of your sample, you can think of it that way. You will get a prediction. This is a single prediction that use m samples to get this result. A prediction, that means you get only one result. But that one result came from bunches of data. Okay. That could be another setting. It's possible. But all of these are pretty much like a setting that you should aware of. It's like a setting that will help you define the theoretical properties that comes afterward. Okay. So we have a reason for it, like why we need to, consider multiple x instead of just one x. And the reason is because, let's say, the first thing first that you can evaluate from your machine learning is the bias. And the definition of your bias is the expectation of your prediction negate your ground truth reference or your reference. And in this case, we will think of it as the noiseless reference. Right. So you can see, if you can calculate the expectation of your prediction, that means you may not just get a single prediction, it could be predictions, right? You get tens of them and you want to find expectation and you want to see how far is that expectation from the reference. That's the first evaluation called bias. And yes, you can calculate the bias empirically or theoretically. If you want to calculate this bias empirically, what you have to do is, of course, remember, how is expectation calculated? Y of y dy integrate. Isn't that right? Yeah. But if you want to calculate them empirically, you can use sample mean. Okay. Sorry, we can do it many ways. If you like. Meh. The reason that I avoid using F is because our machine learning is also represented by F. Okay, that's the reason. But anyway, the key factor is that if you're doing the theoretical method, your P could be different for each of your outcome, Y, right? And maybe I shouldn't use N, I should use C instead. Because the summation go over every possible value of your Y, not your Y samples. But in your sample mean, when you do the sum and divide by the number, it's actually run on the samples. So that's the first thing about empirical versus theoretical that you should be aware of. Don't worry, it's not going to come on your exam. I just want you to know. But in estimation theory, you already got the grades and the score. That's fine. So that's your first evaluation in theoretical sense, bias. The next thing is efficiency, but I would like to skip. because I think efficiency will give you a hard time to understand than the following. No, they're both at a hard time to understand. Sorry. Both the efficiency and consistency. Okay, I'll give you like a rough definition of that. Okay, efficiency is about how many samples that you should use in order to provide an estimation, and that estimation is accurate. Don't worry if you cannot understand anything here. The reason that I would like to skip is because actually I would like to make sure that we cover the important information. This information I actually just provide for those guys that studied estimation theory before, for your information, that you got something that you learned previously and it's kind of make use of it. Okay. And yes, another thing is about consistency. Consistency is the property where you're saying that the prediction result that you get should somehow converges to your reference. So it's about convergence. So don't worry, they're not going to be on your exam. It's not that important in this course, I believe. Okay. Anyway, what's actually more important in this course is the mean square error. Yeah, the mean square error that we've been talked about. But actually there are theoretical mean square error and empirical one. And right now we're going to look at the theoretical. From previously you've seen that when you compute the expectation, there are empirical version and the theoretical version. Mean square error is the same. You have empirical version and theoretical version, but the properties runs the same. That means that you can use your mean square error to tell whether or not you have trained your model enough. And that's actually become like a criteria where normally we'll use to say that we should stop training our deep learning. So that is called early stop technique. หรือพูดอีกอย่างหนึงว่า early stop technique มันเป็นเทคนิคที่ใช้ mean square error นั่นแหละในการเกจว่าเมื่อไหร่คุณควรจะหยุดเทรน just so that they get it quick concept. Okay. Now, anyway, so firstly, if we talk about mean square error, we should recap a little bit. We have y, that is our prediction, the y hat, and we have our ground truth reference. Let's say this time I use y subscript o to refer to the case where your ground truth is noise-free. And when you consider mean square error, be prepared for the fact that your reference may get noisy. So in that case, your y, that normal y, is going to be y subscript 0 plus noise. Notice that I use the capital Y here. And I use the capital Y here. Can someone tell me, or maybe give me an answer, like why would I use the capital letter? Because these capital letters are signifying the fact that they are actually being seen as random variable. Let's say your y subscript 0 is small because it's a constant, it's a ground truth reference, it's noise-free, it's deterministic. But when you add some epsilon noise, then that becomes random variable because this is a random variable. And that y hat become a random variable because your x could be anything. And when you say your x is a representative of a certain categories, there are variations onto it. And that's the reason why we prefer to use big capital letter for x, because your x can behave randomly. Just like what I said, what if we take a picture of a dog? The dog can look ugly, cute, scary, whatever. There are variations onto it. And when we compute the mean square error, be careful. your definition for mean square error will be equal to y hat minus y. That means you include that noise into your reference. Or on the other words, you are considering your measurements or the noisy reference as your reference. You're not considering directly on the noiseless one. Just be careful about this one. Because lots of people, when I ask to derive, and yes, that's going to be one of your exams, derive mean square error and explain the relationship between them. Something like that. So this is the first thing that you should be able to do. You have your y hat, you have your y measurements. Can you derive some properties? Of course, right? We just replace that y hat with the fx, because that's the only thing that is involved, right? And usually as a side note, we may not know the distribution of our prediction y, that y hat prediction here. We often don't know what it's going to behave like. But we have our data. So we can somehow look at the statistical properties of that data, and that's another reason why we rather use fx to represent y hat and do the calculation of expectation based on the properties of x, not y hat. But look carefully that y still exists. Your measurement still living in the equation, right? Because it's a reference. Still saying. But the thing is, if you have a better information about your measurements that is noisy, you can somehow decompose that, right, into a constant plus noises. And that turn your reference expectation from the statistical property of y into epsilon. And for x, it's going to be the same because you haven't done anything to fx. And next, the thing that you would do is that, okay, you may start to, decompose each of these terms mathematically. And for this step, from this line to this line, I would like to beg you to go back home and try to derive. And once you derive, you have the first term that involved with the bias and your noise-free ground truth. Your predictions and your noise-free ground truth. Or on the other words, actually this term. The next term that you will have is going to be your variance. But it's the variance of your machine learning. Be careful. Or in the other words, it's actually your y hat, right? This is the variance of your machine learning. Or on the other words, I could put it this way, like this equation. And the last one, since you have epsilon, somehow you'll be able to get the variance of that epsilon. Or in the other words, it's actually this one, this term. You will get these three terms out of that previous equation. But don't you worry, we have some derivation. What this equation said is that your overall error will depend on the quality of your machine learning that is in this term and this term. The first term suggests how close is your prediction to the noiseless ground truth. The second term suggests how unpredictable it is with itself. Or on the other words, if the variance of your machine learning is large, that means your machine learning tends to give you some random answer. But if it's not, it may not. If it's consistent, that variance should be small. But the reason for a machine learning to behave erratical like that is usually because you have training it for too long. So this is the situation. If you have this high variance, this is one of the situations that's suggesting that you should have stopped your model training now. You shouldn't stay further and keep training because your model is behaving towards your training, not your testing data. And be careful, all of our X and Y here are talking about the input and the output at the testing or validation phase, not at your training. Because you are evaluating your model. Some people are yawning. Are you still with me? Are we still together? Are you going to drop from this class? Don't drop. Stay with me.
Training too long is that word. Overfit is.
Overfitting, yes, that's another word for overfitting. High variance. Overfitting is actually more like the situation where we train too long. But the consequence of that leads to high variance. I'll put it this way. Because high variance simply, the meaning of it is simple. It's like your model behave irradical from the general behavior. Because look at that variance. The reference of your variance is still the expectation of that model. It just simply means that generally it should behave along your expectation. But when that term's large, it's not always the case. Doesn't show. Does it show? Yeah, that's the reference. Yeah.
Y and X in this case is training data or test data.
Y is the testing. Everything that we talk about here is testing, but behavior could be shaped by your training. Because don't forget the fact that when you train a model, you already got an FX. But when you evaluate it on testing or validation. So that X and Y that we are talking about here will be on testing or validation step. Don't worry, it will be on the exam. I'll turn off the light so you get some. จดไปนะคะจดไป Can someone do the screen capture and so we can move on? 1, 2, 3, poof! No. Yes. I will count to 3. 1, 2, 3. I'll assume everyone's finished. Do you all finished? Okay, go. Problem with this mean square error, if we were to do everything in theoretical sense, is the fact that we need to know the probabilistic model of your noise. That means if we know probabilistic model, we can, directly calculate that previous equation. But if we don't, sometimes we may need to use sample means or sample variance. That's what it means. Actually, in a very fundamental level, yes, of noise. But in a more general sense, it's like of your X, noise and X actually. Yep, actually I wrote it here. Okay, this translates into we can use the probabilistic model of epsilon and X to do the calculation if we were to do it in theoretical sense. But if we want to do it empirically, we can use like sample mean and sample variance to represent the mean and variance. Okay? I'll So if we know probabilistic model of epsilon and x, we can actually compute each of these terms, like expectation of the epsilon, the variance, the expectation of the function, etc. That would be easy. But if we don't know, that is more problematic. But usually we will use what we call sample mean and sample variance. So these can be replaced with sample mean and sample variance in an empirical setting or on the words when you don't know the probabilistic model, you don't know the mathematical part of it. That's alternative. Yeah. Shall we move on? Are we nearly dead? Okay, so in fact, that equation that we just seen, how it's derived, could be split into two cases. The first case is where we only consider the statistical behavior of our input x. So in this case, that means your variance of the noise will go to 0, so there's no noise, the other words. And that means that we'll be left with only two terms. Okay, I didn't write it here, but it will just be these two terms without noise for the first case. But for the second case, that is where there are noises, your noise variance will be included into the equation. So that's what it means. But don't worry, there are derivations. So for the first case derivation, it will go in this way. That is, you have your y, big capital Y. That's normally being random variable. This time it will not be random variable because for the first case, you assume that there's no such randomness in your measurements. The only randomness is in your x. And for that, the only problems, or maybe the only factors to your mean square error is going to be your bias and your variance. And actually, this is a formulation that we've seen a lot in estimation theory. We haven't talked about the measurements noises. We only talk about the noiseless reference. And yes, generally, if we don't consider the noise in the measurements and we left with the bias and variance, usually we can use this information to further analyze what contribute to your overall machine learning. For example, if your FX, that is your machine learning, become more complex, or in other words, it's become all fittings, usually it will behave in a way that it has low bias and high variance. This is just information, but we will see example, like a running example. But please don't forget the fact that if your model becomes more complex, sometimes, if the complexity is just the number of iterations, it's fine. Because running more is just the same. The only thing that you lose is the time that you spent on your training. But for some machine learning, more complexity simply means that you have more parameters in your system. So with that, it could actually lead to higher run times and computational complexity in your overall setting. So that's something. Okay. But in this case, it's easier to see that the only two factors leading to your overall accuracy is the bias and variance. For the second case, this is just an example of how you would analyze if you assume that you only want to care about the noise in your measurements and your input is just a fixed deterministic value. So in this case, as you can notice, I will then change my notation from big X into small x, And then after that, I will start compute the mean square error. And as you can see here, yes, you will end up with two terms. The first term is going to be like, I would call it like a bias, because it's like the difference between your deterministic fx and your reference, like your bias squared, plus the noise in your measurements. So what this means is that even if your input is perfect, right, there's no variation whatsoever, but if your your reference has noise, that noise is something that you're going to stay regardless of how well your model behaves. So that's what it means, which is different from what we've seen previously. For these two terms, in fact, what it means is that there are chances for you to reduce the error down, very down, close to zero, because you don't have a constant. Everything depends on your behavior of your model and your data X. So that means that in this case, everything, your MSE, is actually reducible. But in this second case, this term make it irreducible, not reducible. No matter how well your model is, no matter how static your data is, it will stay. So this is going to tell you that if you have been using sensor data in your research, be careful with that quality of your sensor. Because if your sensor is bad, or on the other word, you get the garbage. Whatever garbage in is going to be your garbage out. So that's actually one of the problems that people learned when they start doing the machine learning, is that the quality of their data is not good enough for training a model because they have a very high variance. One way to reduce the variance is, as I mentioned before, maybe you remove outliers manually. Maybe you change your sensor if you can. That could help. No, you're gonna drop. I can see that. That's okay. Yes, it's a little heavy for today. But that's it. We'll go very quick. Okay, so putting two together, we're going to end up with this equation which you have seen before in the previous slides. Anyway, and yes, let's see the example. This example, let's say the first one. Let's say you are using a machine learning to do the, let's say, you could say it's a regression of fitting, that's fine. Right, you're trying to fit a linear model or maybe non-linear model to your data samples. And that blue dot is your training data. If you use a very small number of polynomial parameters, let's say, if your model is like y equal to ax, of course your model is very simple, it's linear. But if you use your model as y equal to a squared x a1 plus a2, huh?
A1 x squared, A1 x squared. If you do the A1 squared, A1 should be constant.
A1
x squared.
Okay, if you want that way. We can do it that way too. Okay, a1 1x squared, like that, plus a2 x1. Oh, don't worry. What I'm trying to say is that, okay, can we go with something simpler? Okay, it doesn't matter what model it is, but what I'm trying to say is that your linear model will look like that line. But if you try to fit in maybe a polynomial function, it will start to behave more and more towards to that green line. And the thing is, the green line, as you increase more hyperparameters, it will fit with your data better. And the reason that I don't write these equations is because many machine learning or maybe model these days could behave just like that. You can use support vector machine, and you can choose like a polynomial order. It just behave like that. If you use neural network, with weights, multiple layers, even though your input is going to be a linear in your inputs, but your parameters is non-linear. It's going to behave like that. Whatever model it is. If you have so many, term, it's still x, but maybe a squared, maybe plus a plus 0, whatever. If it starts to have some kind of non-linearity and your order is larger and larger, I know it's not correct. And I know it should be x1 and x2 whatsoever, but I don't care. รู้แล้วว่ากูผิด Thing is, the larger that order is, the more complicated the model becomes. And usually, if you think about how it behaves towards the fact that it could fit in with all the points in your training. And when it fits with all the points in your training, you can estimate what's going to look like when you do the testing. That means your model will behave rather erratical, and therefore it has higher variance. And when you plot, the training mean square error versus the testing, right? And let's say that where I vary is the degree or maybe complexity of your polynomial order term, which I cannot remember. The more terms that you add, yes, up to a certain point, you get a dip on your performance. That means your bias and variance are getting lower and lower, right? But up until a certain point, when your model is really complicated, your model will start to behave towards to your training data, and therefore your variance will be the one that pushed the error high. So that's what it means. So what it means that, and in fact, you should stop at about this order of complexity. Don't go beyond. Because going further beyond means nothing but your model behaving more like your training, and it's no longer representing your testing. And that go back to the first lecture that we've done today, is the fact that when you distribute your data, when you split it, you should make sure that you split it evenly. Because otherwise, whatever you train your model in your training will not behave in a way that it could be used with your testing or your validation. So data splitting is another thing that's goes together with all of these. มีคำถามไหม Any question? จะหมดเวลาอีกแล้วอะรู้สึกว่าพักนี้พูดช้าเรื่อยๆอ่ะ So that is why knowing about the mean square error, bias, and variance is somewhat important. And when people say your model have low bias, really means that it actually have low error with respect to your ground truth reference. But the thing is, what you see at the end is going to be like curved like that. How can you tell which one is from the bias, which one is from the variance? It's hard to tell, in fact, because even up until this point, it's a combination of those two terms. And sometimes it's three if you have like noise in your measurements. So it depends on how much combination you have. But when your mean square start to rise up in your testing or in your validation, that simply means you should stop increase complexity to your model. And yes, actually this one I adopt from อาจารย์จิตรมุตนะก็คือ it's actually like a graph, maybe relationship between your model complexity, your bias, right, and your variance. Of course, higher complexity lead to higher variance. But at the same time, when you have higher variance, even though your bias may be low, but it's hard to start to interpret what goes inside. Just like today's when you use machine learning, especially the deep learning. How can you tell what's going inside when your model is like polynomial with something and multiple layers? And with that, sometimes people will start trying to use other tools, like what we call GradCam. Have you know it?
Yeah, from you.
Yeah, for me.
Estimation theory.
GradCam is like a way people use to analyze what goes inside your machine learning. Because usually your model is going to be too complicated to understand. So anyone here use deep learning? Raise your hand. I know that too. You use it. Maybe try using this tool to visualize the attention. Or maybe, it's like the intermediate result at each of your layers, because that sometimes resonates with your targets. It could help, but it may not help. And that's another reason why, aside from bias variance, which you can see that is actually a very rough term, people start new field these days that is called AI transparency. It's actually like a field where people start to try to find a new way to analyze what's going inside a very big deep learning, each of its layers, so that they can understand what's going on, like whether or not they're using the right data, or whether or not they are doing something that is, going to the opposite way they want. Or maybe they capture information that should not be capturing, but somehow that information helped. So yes, feel free to look at it. Oh yes, another maybe keyword is explainable AI, like explainable, like this one down here, explainable AI. Yeah. Another term about this, science of understanding what's going inside deep learning. But of course, for our course, we will look at the simple bias and variance, and that's it. Okay, so coming back, GradCam, explainable AI, that tool will kind of help you interpret your model better. That's it. It's only allow you to visualize what's going inside. It doesn't help with your complexity, but it can help if you start to see that your model are behaving something rather hard to understand, and the complexity is very high. Maybe you start to think about reduce your complexity and see if it's still working. Another way that I sometimes use to see if the model is having high variance, and maybe some of my students will see me do it, is to ask them to run that model multiple times with that testing and get your testing shuffle a little bit and see if they still get the same result. Because if they get a very weird result once you shuffle the data, simply means your variance is getting high. That means your model is fitting towards your training and is behaving towards something that you thought previously it works, but it doesn't. That's another way to check the variance. On the other word, just do multiple runs with shuffling on your testing. These are the experiences, not going to go on the exam. Okay, my experience. มีอะไรไหมเหมือนอาจารย์ทำอะไรผิดป่ะยศพัฒน์มีป่ะ Nothing แหมกระซิบกระซาบอาจารย์เป็นห่วงเลยนะlast one. No, we are not making it. Okay, maybe next time we will talk about and very quickly about the model selection, but not today. Okay, the last set of things that we have to know is the evaluation with your data samples. This time, let's on the theoretical side, we can go really quick, very fast. But for you to know, most of them are just terminology. All right? You should remember some of them, but not all of them. Don't need to. The one that actually important is R square. The last one, R square. And RSS. The rest of that, if you can partially remember, I think you just do the one cheat sheet, write it down, and prepare for your exam. Okay? But these two have to go inside your cerebellum. ไฮฮิปโปโปแคมมัสอะไรก็ไม่รู้ละเต็มไปหมดเลยแต่ไม่ได้เรียกชีวะนะเอาเถอะ let's start from the first one. Residual sum square. By definition, is a sum of the residual. And if you look at the formula, that's it. Where m is the number of samples that you get from each run. Let's say if you know that y hat is the samples of your y hat, your prediction. You run one prediction, you get two predictions, you get three predictions, you run each time m times, yes. And yes, of course, that m times. Sometimes if it has some kind of measurements associated, okay, yeah, that noisy measurements and stuff. And look carefully. I use y, not y subscript o, simply means whatever you're measuring against as your reference here is noisy. It's a noise-free reference versus your predictions. And you just sum and square.
It's the same as mean square error, but not mean, but just sum.
Just sum, yeah. So that by definition, there will be. This one, no normalized, simple RSS. When people talk about RSS, it's this. But there will be RSE, the one that you just mentioned, with the normalized version. But I write it down. Yeah. Okay, before we go to that RSE, or should we go to RSE? Okay, we go to RSE. RSE, the residual standard error, is the one where you normalize with the number of samples minus your model complexity. P is actually, let's say, if you have been using 5 model parameters, just like our previous example, like 5 and 17. For one case, 5 can be 17, another case, 5 can be 17, or maybe 1. If you use linear model where you only have AX multiplied, is 1. Actually, this term is added to help with the biasness of your estimator, but please don't worry, it's just a formula. You can remember this formula and that's it. But for those that study estimation theory before, it's just like your sample variance formulation with P equal to 1. Just linking information. Yeah, that's it. Yeah, that's your RSE. Problem with RSE. Yes, it's just like our previous RSS. It's sum square, right? You cannot tell whether or not this is a big one, small one, or whatever. So that's actually caused some kind of problem, and that's the reason why we have to look at what we call R square. That R square will have some kind of normalization called TSS. And TSS is pretty much the sum square of your reference, but with the expectation of it. So you have your reference, you do this sum square, it's like you compute the magnitude of your reference. So you know at least generally how large that is. And you use it as your denominator. And you have RSS on the top. And that will help signify how big is your RSS versus the size TSS. So that's what is R square. In fact, this is the end. I don't want to teach you the other two, but I can go to other two because we have some times. Because it's not that important, but anyway. RSE, R square, RSS are actually the 3 important things that you should know after today lecture. Yep. You can read the description below. I actually refined it already, so it should work. And yes, one thing, your r square has a value between 0 and 1. And another thing is that when your r square is high, suggesting low error. Recently, there is a researcher from some university reporting a very, very low r square, and it's telling us, we have high accuracy. And we all, so he doesn't know what is r square, or he forget to do the minus 1. So he probably forget to do the minus 1. Anyway, if your r square is high, you have low error. Closer to 1, low error. Because if you just imagine r is equal to 0, then that means 1 minus 0 is 1. Okay, that's it. Are you thinking about withdrawing? Not yet. Just side notes, not that important. The standard error. Standard error is pretty much like, I want to call it like a variance. Yeah, it's a variance. It's a variance of your predictions. That's it. You can compute it very different way. Actually, I write down how SE could be computed, especially when you involve with, the algorithm that actually have to sample your data. The example is in the next page. But anyway, since many of you haven't take the course on estimation theory, I'm really afraid that if I talk about it, it's going to get really confusing. But anyway, just know SE is like you computing the variance. And it's more like empirical variance. If you look at the formula, this expectation of the sum of the square error, right? And your y bar is actually the expectation of y hat. So it's a variance. Yeah, that's all. Okay, thank you for your attention today. And I would like to tell you that maybe next Monday, please bring a computer and you can actually construct a group on your my course view, right? Yeah. คณาวุฒิกรุ๊ปเพื่อนให้หน่อยนะหมายถึงว่ากรุ๊ปของหนูนะเพราะกรุ๊ปของหนูเป็นกรุ๊ปโดดเดี่ยวมากถ้าใครยังไงก็ yes it's up to you who you want to group with actually I told the students that I would like to make like no more than 5 groups and at the moment I think there are already 5 groups. But you can ask each of them if you want to sit in with, if you can have more than 5 people for each group, that's fine. If I don't know, but depends. Anyway, if you already make up your mind about the groupings, please put it on my course view. Be careful that your friends shouldn't be in 2 groups. I mean, if you want that one friend in 2 groups or more than 1 groups, I will put this way. I mean, his score would not get increased from living in multiple groups. I will just do the scoring, maybe do the argument. Sorting minimum and just use that one. Just kidding. Anyway, stay wherever you like. Yes, so in this course we have 50% for homework, and that homework shall be done in groups. I don't want to collect everyone's homework. It's scary for me. I've done it before. I understand what it's like. And we have 2 exams, that is the midterm and the final. For the midterm exam, we will do it in the time, like in the time where we will do the lecture on that week, that 2 weeks. That's it.
ปีนี้มิดเทอมมันเร็ว
ฮะ
มันปีนี้มิดเทอมมันเร็วหรือว่าปีที่แล้วมิดเทอมมันช้า
มันไม่เร็วมันไม่ช้าแต่เราอยากให้เป็นอย่างนี้ And yes, the same thing probably happened for your final. Because we have so many wrap-up lectures, that means we have times. I'll think about it. I'll see what it's like first for your first trial, and if it works, we will go with it. Because I don't want this lecture to be too heavy for all of you. Okay. And yes, you can look at the homework 1, 2, 3, 4, 5 schedule. It's actually on here. And I have already set up the deadline for each homeworks. Actually, all of them are having some kind of deadline that I set up. So yeah, you can set it.